For our independent t-test example, I've given you guys the research scenario that Professor Valenzuela wants to know if taking physics prior to taking Kin 300 has an effect on course grades. He surveys 39 students who volunteered to participate to find out if they have taken physics or not. Then he records their biomechanics grades at the end of the semester. So this automatically tells us, based on our information, right, that the effect we're interested in is taking physics. So whether you've taken physics or not, those are two categories or nominal variable. And if that manipulation of taking physics or not has an effect on course grade. So course grade would end up being our dependent variable. Okay. Because we have mutually exclusive groups or between subject factor in terms of if you've taken physics or not, that tells us we have a between subject variable, which is why we are running an independent t-test. So let's go ahead and head over to our output. We have our group statistics, which we'll end up using to calculate our effect size. And then we have our independent samples t-test. So recall that when you're first looking at your output, you have to make sure you've met your assumptions first, which is where we look at Levene's test for equality of variances, or this is our homogeneity of variance assumption. So in your guys' practice questions, I've asked you to identify the p-value for, identify and interpret the p-value for homogeneity of variance. So under Levene's test, we could see a p-value of 0.680. Okay, so p is equal to 0.680, which is greater than 0.05. Therefore, we accept the null hypothesis. And remember, the null hypothesis for homogeneity of variance says that we have equal variances between our samples. So we can meet that assumption and say there are equal variances between samples. Okay. For the main effect, we're interested in looking at the p-value for our t-statistic. So in this case, go back to our table. We can see our t-test for equality of means. We can see our t-statistics, and then we can see our p-values listed here. Now, because we said we are assuming equal variances, we would read this top row, and that would end up telling us that our p-value is equal to 0.105. So p is equal to 105, which is greater than 0.05, which tells us that we should accept the null hypothesis. So interpreted in the terms of our variables measured, we might say that taking physics has no significant effect on a person's biomechanics grade. Okay. And then I've asked you guys to identify and interpret Cohen's D size effect, or Cohen's D effect size. Okay. So the identification is actually the calculation of Cohen's D. And then I've asked you to round your answers to 2 decimal places. So we're going to use our group statistics. And I'll open my data spreadsheet. Okay, so in order to find Cohen's D effect size, we need to indicate what our descriptive statistics are, and then we have to calculate the pooled standard deviation and then incorporate that into the mean difference divided by this the pooled standard deviation. So first things first, let's kind of copy some information over from our output. So let's do this here. I'm going to say that this column is going to be my statistics for people who haven't taken physics versus people who have taken physics. we need to know the mean, standard deviation, as well as the sample size. So from our output, we can see the mean of people who haven't taken physics is 79.7864. The mean for people who have taken physics is 82.6. Standard deviation for no physics is 5.11639. And standard deviation for people who have taken physics is 5.3905. And then we had 22 people who haven't taken physics, 17 people who have. From here, we can start calculating the components of our pooled standard deviation, as well as our mean difference, and these are the values that end up going into our effect size calculation. So the mean difference, we just take the absolute difference between the means of both groups. And then for the pooled standard deviation, I'm going to do, I'll say standard deviation pool numerator, standard deviation pool denominator, and then we'll kind of put everything together into the effect size calculation. That way we don't get lost in all of like the parentheses that we need for all of these equations. So the standard deviation, or the pooled standard deviation, is the square root, and then in the numerator we're looking at standard deviation squared times n minus 1 for each of our samples. So I'm going to put equals, and then a set of parentheses for sample 1 and a set of parentheses for sample 2. From here, I'm indicating that sample 1 standard deviation is squared times the sample size minus 1. Add a parentheses, and I now have my first sample kind of enclosed in its own set of calculations. In my second set of parentheses, I do the same thing. So standard deviation of sample 2 squared times the sample size of sample 2 minus 1, and add a parentheses. So this is the numerator in our pooled standard deviation calculation. The denominator is just our degrees of freedom for our samples as a whole. So we take the total sample size, whoops, wrong button. Total sample size plus, there we go, minus 2, since we have independent samples. And then our effect size is going to be the mean difference divided by the square root of our pooled standard deviation numerator divided by the denominator. And then I've specifically asked you guys to round your answer to 2 decimal places, so we get an effect size of 0.54. Okay, so Cohen's D would then be 0.54. And the interpretation of that is that there is a medium effect size in biomechanics grades between students who have taken physics versus students who have not. Okay, and that is our example for our independent t-test. Our last video will cover our paired samples t-test.